All right. The next talk in our session is lexical effect handlers directly. This will be presented by Kong Ma.
Hello, audiences. Today, I will show you our recent work on compilation of lexical effect handlers. This is a collaborative work with Zhao Yige, Edward Li, and Yizhou Zhang. Effect handler is a powerful language feature that allows programmers to write programs with interesting control flow. It subsumes many popular language constructs like async await, coroutine, and generator. The dynamically scoped effect handler suffers from a modularity problem, and there is a recent line of work that gives lexical semantics to effect handlers, which restores modularity to the program. Lexical effect handlers are expressive. They have been implemented in languages like Effect and Coca, and can be generalized to manage bidirectional control flows. Before we dive into details, let's first get ourselves comfortable with the operational semantics of lexical effect handlers. I'm going to show the source code on the left and a runtime turn on the right. As the control enters the handled body, we freshly generate the label 314, which is going to identify this handler instance. The label is also substituted into the handled body. Next, a raise expression is evaluated. The raise expression indicates which handler instance it raises to. The continuation is captured and is substituted into the handler implementation for K. Finally, we reduced a resume expression. The first argument is a continuation, and the second argument is a value. After the reduction, the whole of the continuation is filled with the given value. And that concludes the demonstration. The lexical effect handlers, being an attractive language feature, still doesn't have an efficient implementation. As you will see shortly, the current implementation suffers from a scalability issue. The program on the left is something that could be written by a real-world programmer. It shows a recursive function where the body of the function is wrapped inside an exception handler. The function can also raise login effect, as is indicated by the function signature. Effect with a K is a state-of-the-art language with lexical effect handler. If we run the program without the login effect, this is what the running time looks like. The x-axis is a plot in the input size, which corresponds to depth of recursion, and the y-axis is the running time. If we turn on logging, the running time becomes the line in red. It shows a polynomial scaling trend, which is not ideal. In this work, we implement a compiler for our language Lexa. We're able to achieve linear scaling trend with or without the logging effect. For this particular program, Lexa also runs a lot faster compared to Effect if you look at the y-axis. However, we want you to only pay attention to the scaling trend, as the scaling trend manifests the difference in our compilation strategy, which is the focus of this talk. In this work, we show how to compile high-level modular algebraic effect in Lexa to low-level swift stack switching in assembly. Our system finds the handler in constant time and captures the continuation in constant time. We thus claim to be more scalable than existing solutions. To understand why there is a scalability issue with existing compilers, let's see the concrete execution of this program. I will illustrate the evaluation context on the right as the program runs. Before we enter the function, there is already a logging handler installed on the evaluation context with a freshly generated label 123. As the program runs, we install a sequence of exception handlers on the evaluation context. When an effect is raised, the operational semantics indicates that the closest enclosing handler that matches the label 123 is used to handle the effect. Finding such handler requires a linear search of the evaluation context, which is costly and is a source of the scalability issue that we just saw. There are compilation strategies that avoid the use of labels, but it still exhibits a searching behavior similar to this one. Searching for handlers seems to be at odds with the spirit of lexical scoping. Lexical scoping is all about statistical reasoning. It's about knowing things at the compile time. Searching for the lexical handler at the runtime feels unsatisfactory. This unsatisfaction is resolved when we compile to low-level languages. We no longer need labels. Instead, every handlers naturally have a memory address, which we use to identify handler instances. Consequently, we can reach a handler in constant time. To see how we apply that insight in practice, I will show you how we compile the effect handler constructs into assembly sequences that manipulate stacks. First, let's look at a function without effects, just to get you comfortable with the animation that I will use throughout the presentation. This function in Lexa simply performs addition. The function is compiled to the assembly sequences on the left. We will see an illustration of stack in the middle and the register files on the right. As we enter the function, the arguments have been pushed onto the stack. We now execute the instruction highlighted in yellow. The red arrow indicates the position of the stack pointer. The stack grows downwards from bottom to top. First, the addition operands are loaded into register R1 and R2. An addition is performed with the result stored in R1. Then, to translate the light binding, the result of the addition 43 is pushed onto the stack. We then load the 43 back into the register R1 as the final value of the function. After that, the stack is popped, and the return instruction is executed with the return value in R1. Now let's look at an Lexa expression that uses all effect handler constructs. The compiler provides 3 built-in assembly instruction sequences that could be called from other places. We will show their implementation later. Let's first look at the compilation of the handled body. Among them is a raise expression, which is compiled into 3 lines of code. The handler reference is moved into R1. The argument, a unit, is moved into R2, and a call to raise instruction sequence is made. The resume expression is compiled in a similar way. The entire handle expression is compiled into 3 instructions. The code location of the handler and the handled body are moved to R1 and R2, and a call to enter is made. Starting from this point on, let's see the actual execution of the program. The control is now inside the instruction sequence enter. You don't need to pay attention to the assembly sequences. The animation is sufficient to understand what's going on. We first allocate a new stack using the assembly instruction make stack. We then push the handler function onto the stack. And then we push the pointer to the top of the previous stack. We will call the first 2 slots of the stack the header frame of the handler. They include necessary information for the handler to carry out operations. Finally, the control goes to the handled body. The only argument of the function, which is a pointer to the header frame, has been pushed to the stack. This value is going to be passed down to the call chain to every function that will potentially raise to this handler. The control is then transferred to the body function. Now we're inside the body function, and say that we are raising to the handler that we just installed. As the semantics dictate, we're going to capture and reify the continuation. This is done by the first part of the raise instruction sequence, which perform an exchange between the stack pointer and the header frame. Now the header frame no longer points to the previous stack. Instead, it points to the end of resumption, which in this case is the top of the current stack. We then malloc a single element tuple to store the pointer to the header frame. This single element tuple will be used to represent resumption. We use this in direction so that we have a way to invalidate the resumption after it is used. Although our formalism only supports single-shot resumption, our compiler implementation supports a limited form of multi-shot resumption. Finally, we are ready to jump to the handler implementation. R1 stores the first argument, a unit, and R2 stores the second argument, which is the resumption. R4 is the jump target. Now the control is inside the handler. Let's say that we are at the beginning of the resume instruction sequence, which is going to resume the resumption. At this point, R1 stores the argument to the resumption, and R2 stores the resumption. We first load the pointer to the header frame into R3. And then we override the single element tuple with a special token to prevent the resumption from being used again. Next, we perform an exchange between the stack pointer and the header frame. The stacks are, in a sense, linked again. With an execution of the return instruction, the control goes to the top of the resumption stack, effectively resuming the computation. As you may have noticed, the handler in this program resumed the resumption in tail position. This means that resumption is not used in any interesting way. Consequently, we don't need to allocate a new stack when we enter the handler construct. The Lexa compiler will instead allocate the handler's header frame within the same stack, saving an allocation. Lexa compiler carries out the same optimization for abortive handlers, which are handlers that do not use resumption at all. We formalize the operational semantics of the source and target language and prove that compilation is semantic preserving. The proof uses a canonical simulation argument. You can find more details in the paper. On this page, you see the architecture of Lexa compiler. The Lexa source code is first compiled to C, then combined with assembly sequences that you just saw. The program is linked to a garbage collector and sent to LLVM for optimization and native compilation. Please check our paper for discussion on implementation techniques. In particular, there is a discussion on using calling convention instead of using set jump long jump, and consequently allowing the compiler to do more optimizations. We evaluate Lexa on a set of community-maintained benchmarks. We also added a few benchmarks that represent the real-world use of effect handlers. In the next few slides, I will share with you interesting findings using a few scaling plots. Iterator is a simple program that uses a handler in a tail resumptive way. The Lexa running time looks flat because it is indeed flat. The Lexa compiler compiles program to a constant. This is in part thanks to the optimization done by LLVM, but it also shows the quality of code generated from Lexa. Resume non-tail2 is an artificial benchmark that checks how efficient a language captures continuation. The plots are split into two for easier visual comparison. Coca has a polynomial runtime trend because it builds continuation frame by frame. OCaml is stepwise linear because it copies and doubles the stack upon overflow. Effect compiles by CPS, so no extra effort is needed to capture continuation. Lexa uses segmented stacks, so also no extra effort is required to capture continuation. Interruptible iterator is adapted from previous work. It allows the client code of a coroutine iterator to concurrently update a list during iteration. The program installs deeply nested effect handlers, similar to the one we saw before. Effect has a polynomial scaling trend, as it performs a linear search on every race. OCaml also has a linear trend, as it also performs a linear search on every race, as is dictated by the semantics of dynamically scoped handlers. Coca avoids linear search with tail resumptive optimization. Lexa achieves linear scaling because it raises effect in constant time. I hope you enjoyed this talk. The Lexa compiler is open source. It is still in the early stages, and we're adding exciting new features. So expect to see more Lexa talks in the future. Thank you.
All right, so we have time for some questions. I will start with one. Can you talk about, so first of all, this is really cool. It's great to see excellent performance. I guess the second result in this sequence talking about performance. But especially with the challenging semantics here. But one of the, I was curious about the limitations with multi-shot, right? So under what circumstances can you support multi-shot continuations?
Yeah, great question. So the difficulty of supporting multi-shot resumption is that we basically pass down a pointer to the header frame down the stack, right? So that's a pointer into the stack. And when you copy the stack, you copy the old pointers. So that results in a sharing of the header frame of the handler. And consequently, we have a limitation of you can only resume one copy of a resumption at a time. You can't have two active resumptions at the same time because that will result in sharing and each invalidating each other's header frame.
I see. So is that something that can be checked in a discipline by the parser or by a type checker, or is that something the programmer has to follow?
Yeah, it's something that programmers has to follow. This work doesn't have a type system. It's about compilations.
Sure.
So sorry.
Future work, perhaps.
Yes.
Yeah, interesting.
Sorry if this is a silly question, but just to follow up on that, does that mean that in principle, or rather in the language, it does not restrict the use in multi-shot contexts, but it is the programmer's responsibility to ensure that the shots don't occur at the same time to avoid like undefined behavior or something?
Yeah, basically our source code will get stuck if you reuse resumption twice, right? So yeah, if you do that, your program will get stuck or go into undefined behavior. We prove our simulation based on that, right? If your source program doesn't get stuck, the targeted program also doesn't get stuck.
Thanks.
Okay, thanks for the talk. I agree with you that this is the way lexical effect handlers should work, and I think this is the way effect handlers should work. We shouldn't use dynamic scoping, right? This is
Great.
something we learned from history. But I'm a bit concerned about the multi-shot thing. So can't you at least check at runtime that this does not happen? We don't want undefined behavior, right?
Well, yeah. There's actually I should say that as it probably illustrated in the animation, we override that single element tuple with a token, right? So we could just let the compiler abort if they see that token. But it's a small change. I think we can easily implement that.
Okay, so that's good to know.
Mm-hmm. Thanks.